So I would like to start by thanking the organizers to provide this opportunity, especially in this time due to Corona. This is a great conference so far, and thank you very much. So my talk is on symmetries of Einstein-Weyl manifolds with boundary, and it's a paper that's submitted on arXiv, and this is the number, and also it's submitted for publication, but it is not yet published. My talk will be first, I will talk, give some background, then I will review a twister construction done by Dr. Borufka, and then I will state my results. First, I will give the definition of Einstein-Weyl manifold. We have a manifold M with a conformal structure, which then it will be a conformal manifold with a compatible torsion-free connection D, which is a Weyl connection. Then the trio will be called an Einstein-Weyl manifold if the symmetric trace-free part of the ridge tensor of D vanishes. And in 1967, Penrose started this twister theory as because in physics we had quantum mechanics and gravitation, which was given by Einstein theory. But these two, as we know, are not very much compatible in many cases. And one direction that Penrose proposed was that we also quantize the space-time. So if we have quantum field theory, which is quantizing the fields, let's also quantize the space-time, and now we can have a quantum theory for both of them together. So twister theory started with that, and later in 1982, Hitchin obtained a similar correspondence between three-dimensional Einstein-Weyl spaces and mini-twister spaces, and which can be summarized in this theorem. So let this O-1 be the tautological boundary over CPN. The theorem states that we have a surface T, and there is a family of non-singular holomorphic projective lines, each with normal boundary isomorphic to O2, and these lines will be called mini-twister lines. Hence the name mini-twister space. T has and this surface has a real structure which uses the antipodal map of CP1 on lines from the family that are invariant under this real structure. And then it was shown that the parameter space of these lines in that surface is actually a Einstein-Weyl manifold. Later in 1985, Jones and Todd related the work of this correspondence by Penrose and the correspondence by Hitchin, which now I hope I can say here. So we have this, let's call it, I don't know. Can you see? No. Ah, yes. So this is the work by Penrose. So we have this sorry. This anti-self dual space time, and then we have the Hitchin correspondence. So here we have the mini-twister space, and then we have the Einstein-Weyl. So this upper part was the work of Penrose, and the lower part of the diagram was the work of Hitchin. And Jones and Todd showed that we have this diagram and it's actually commutative. On this talk, I will take only these parts. So I'm only talking about the mini-twister space and Einstein-Weyl But if you look at the paper by Dr. Borufka, which I will show in the references at the end, then you can see that also this whole diagram kind exists for this construction.
Right.
So as a definition of a conformal Cartan connection, we have n manifold sigma, and which has this quadrupole, where V is ranked n plus 2 vector bundle with inner product or sigma. We have a null line sub bundle over sigma, which is called lambda, and we have the our linear metric connection on V, which satisfies the Cartan connection, hence the name conformal Cartan connection. And this is the condition that it should satisfy. So this epsilon should be isomorphism from this manifold to this one. So as a review of the two-star construction done by Dr. Borufka, first let's start with having a real analytic surface M with Cartan connection. And if we complexify it, then we obtain a complex surface sigma with a complexified Cartan connection as this, which in this case, the lambda 0 will be annihilator of lambda for each point at sigma. We will have two null planes which are defined as solutions to this equation. And we have the epsilon, which was given in the definition of Cartan connection. And as a result, we can have two line subbundles T plus and T minus of the tangent bundle T sigma, which are defined in with these conditions. And we have two families of curves, which are defined in a way that they are the integrals of those of T plus and T minus. So T plus and T minus are the tangent space to the curves. And we have two fiber bundles, which are given by the projectivization of these planes. So at each point we have these two null planes. It gives us a fiber bundle, and then by projectivization of those, we get these fiber bundles F plus and F minus. Now, on the base of the bundles, we had the surface sigma, and we had the family of curves there. So now we can horizontally lift them, and lifting them will, the lifted curves will foliate the total space of the bundles F plus and F minus, and the lifted space of the foliations is a manifold which is denoted by T plus and T minus respectively. Since well, each curve will have its horizontal lifts, and it will define a projective line in T plus and respectively in T minus. And because of that, we will denote them by the L plus C plus, and it's the same L minus C. But since at each point, these curves are intersecting each other on sigma, so we can change the notation and just denote them by the point of intersection. And these intersecting lines later we will say that they are corresponding to the points at the boundary M, which I will define later. And first, we restrict the manifold sigma such that the horizontal lifted curves from each family intersect each other at most once. And the point of intersection will be denoted by sigma, and this relation will hold. So this is where they are intersecting. And now using this, we can glue these two manifolds together to get the manifold T, which will be the mini twister space. And to show that this is mini-twistor space, it is shown in the article by Dr. Burfka, and I won't go into details. But if you want to look further, you can look at that paper, and it's shown that this is actually a mini-twistor space. Now, where comes my actual work? So I start with a symmetry on the starting real analytic surface M, which we had. And then so we have a vector field on this curly M. And then we complexify it to have another vector field called X, which will be on the complex surface sigma. And that X will have a flow, which will use this local one-parameter group of local transformations. And as a definition of what we call a symmetry of conformal Cartan connection, this is as follows. So the Cartan connection is preserved by phi of t if and only if the following holds for sufficiently a small value of t, which is because this phi of t will be an isomorphism. So it is called a symmetry of conformal Cartan connection if it preserves the line bundle lambda, it preserves the inner product, and also it preserves the connection. Then it will be called a symmetry of conformal Cartan connection. Now, we had two fiber bundles, U plus and U minus, which were defined pairwise by those null planes, which were the solution of that equation. And we show that this phi of t, which we start with, preserves these fiber bundles. It also will preserve the line subbundles of the tangent bundle, and this part comes from that it preserves the inner product. Also, this transformation induces another transformation on the fiber bundles, and that one will be denoted by phi tilde. And we show that this preserves also the lifted curves. Furthermore, it is compatible with the gluing that we did, and so it extends to the mini-twistor space T. So now we started with the base, and now we get a symmetry on mini-twistor space T, which also preserves the real structure. So it actually will preserve the real mini-twistor lines because of that last point. The obtained transformation descend to transformation on T plus and T minus. So it is important that now that we have the transformation on two pieces T plus and T minus, they were glued to each other to get the T. Now the obtained transformation also preserves this. So we get actually a symmetry on the whole mini-twistor space. And that will be denoted by phi prime. So now actually we started from the base, and now we have a vector field on the whole mini-twistor space T. As a definition of symmetry of Einstein-Weyl manifold, so let us have the Einstein-Weyl manifold as defined earlier. A diffeomorphism is called a symmetry if it preserves the Einstein-Weyl structure. So we had a manifold with Einstein-Weyl structure, and now if we have a diffeomorphism that preserves this part, then it will be called a symmetry of this. And we have a manifold M, which is a complex three-dimensional manifold, and with a Weyl structure. A null plane is a two-dimensional subspace of the tangent space at each point. if this conformametric degenerates on that subspace. Or you could say that this subspace is the tangent to the null cone of conformametric. Furthermore, a null surface is a two-dimensional submanifold such that for every point, the tangent space is a null plane. Now, let T be as before the Mintuster space and M the corresponding Einstein-Weyl space, which we knew from the heating correspondence. So M is a complex three-dimensional manifold, and the points on the Einstein-Weyl space correspond to the Mintuster lines in T, and the points. So it makes sense to use this notation as we have a point here. It corresponds to a Mintuster line there. And we will have two families of submanifolds defined as follows. So we have the points such that, and the points give us the line. So if we take the points on the line, then it will give us, this will be the two-dimensional complex submanifold of this three-dimensional manifold. And we have this another submanifold, which is this one is one-dimensional. So we have 2 points on that line. And the complexified Einstein-Weyl structure and the complexified Einstein-Weyl space will be as follows. So we can say that Einstein-Weyl structure can be given as this proposition. That's these two, the first family here, and the set of null surfaces of this conformametric coincide. The second is that this submanifold and the set of geodesics coincide. And the third condition is that a curve is null geodesics if and only if that point is a double point in L. Or we have these two, in another saying, we can say that these 2 points are infinitely near each other. So we obtained a vector field on T, and now we want to show that this is actually a symmetry, extends to symmetry of the Einstein-Weyl manifold. And this is done the way that we show that in our article that this vector field, the flow of this vector field actually will preserve these 3 points. So it will preserve the Einstein-Weyl structure, hence it will be a symmetry of Einstein-Weyl structure. Remember, the symmetry of Einstein-Weyl structure was a diffeomorphism that preserved the Einstein-Weyl structure. So now to show that it preserves these 3 points, we actually have shown that, and now we obtain a symmetry on the Einstein-Weyl structure. So to put it together, we started with a symmetry at the base. Thank you. We started the symmetry at the base. This space is actually shown that we have, when we have this Einstein-Weyl manifold, this base that we started with, it's actually the boundary of that manifold. So we start with the symmetry on the boundary, and then we show that this actually extends to symmetry in the bulk. And this is actually what happens in this second last theorem. So if we have a real analytic surface with conformal Cartan-Cochin and symmetry Z, and we have vector bundled V, which was given in the conformal Cartan connection definition, and M be the Einstein-Weyl manifold constructed from this real analytic surface. Then there exists a vector field on the whole manifold with the boundary, such that its restriction to the boundary is actually what we started with. And these two are the compact result of the paper. And these are the references. This first one is actually the main part, that's the twister construction done by Dr. Brufka. And thank you very much.